pi epsilon 0, Q1, Q5, no, Q2, Q4. Divided by R24 plus 1 over 4 pi epsilon 0, Q3, Q4, R34 plus 1 over 4 pi epsilon 0. Well, that's it. No. And you have to bring all the charges one by one. So let's just write it in a shorthand notation. So let's skip this. The total potential energy of our system should be equal to, well, let's say that we brought the charge Qj. We are bringing the charge Qj at some point. Now, all the other earlier charges have already created some potential at the point where my charge Qj will arrive. So the energy, the work I have to do in order to bring this charge Qj to its final point is 1 over 4 pi epsilon 0 Qi divided by Rij. But of course, I should sum over all the charges already existing in the system. So I should be less than J. Is this point clear? I'm bringing, let's say, if you look at the explicit expression, when I'm bringing Q2, I only have Q1. When I'm bringing Q3, I have Q1 and Q2. When I'm bringing Q4, I have Q1, Q2, and Q3. If I would bring, let's say, Q5, I would have Q1, Q2, Q3, and Q4 terms. So this notation just makes sure that I only have here, in this sum, I only have contributions from Q1, Q2, Q3 up to Qj, not including Qj. Then, of course, I have to bring all the charges. J, I don't know how many charges you have, let's say, from 1 to n. Let me also write this in another form. Is I starting from 1 to j minus 1. This is the sum I have. Well, rather than writing these two sums explicitly, I usually use a shorthand notation. This is equal to I sum over all I and j's such that I is always less than j. Both go from 1 to n, 1 over 4 pi epsilon 0, qi, qj divided by Rij. This is the total electric energy of my system. Total electrostatic energy of my system. So, for example, if you imagine that all these charges are positively charged, that means that you are kind of you should be exerting some force to hold all those charges at that region. If you release that force, if you release your system, all the charges will just release its energy and you will get all these particles moving out with a large kinetic energy. So that's kind of, you are taking back the stored potential energy. Now you can even convert it a bit further. You can write, okay, U is equal to I less than J 1 over 4 pi epsilon 0. Well, this is also equal to sum over all I and j different, not necessarily smaller, not necessarily larger, 1 over 4 pi epsilon 0, qi, qj divided by Rij with a factor 1/2. Now, why 1/2? For example, if you look at this first expression, you have a contribution from Q1, I is 1, J is 3. So you have Q1, Q3 term. If you look at this expression, you have a term I1, J3. You also have the term I is equal to 3, J is equal to 1. So you have the Q1, Q3, and also Q3, Q1 terms. You have two terms, but they are basically the same. So you have to divide by 2. Again, this expression, again, tells you how much potential energy your system has. Which you can also write as 1 over 2 sum over I, Qi, V at Ri. This is the electric potential at the point, at the position of the charge Qi created by all the other charges. You can also use this expression to calculate the total energy of the system. This one, you will see it. This is what we would like to use, this expression, because V is kind of easier to evaluate. Rather than evaluating this for each J, evaluating a sum that contains a different number of terms, you just calculate this sum where the VRI, where each sum contains equal number of terms. This is easier to evaluate. We will see an example of that in a few weeks. Other questions? Well, that is why I converted it into this expression, by the way. It is easy to write this V as an integral. So let us do that. Suppose we have not these point charges, but I have a region of space which is a charge. And the charge is somewhat distributed. And if you take some volume of charge, some volume inside this charge distribution, let's say delta V, the amount of charge in that volume, let's call it delta Q, will be some function of the position times delta V. This is what we call the charge density. So it gives me the amount of charge per unit volume. So in most of the examples that we will be dealing with, we will be assuming that the charge density is, the charge is either uniformly distributed over some volume, or it is uniformly distributed over a surface, or it's uniformly distributed over a line, in most examples. There will be a few examples where we will take that the charge density is not uniform. But let's just assume we have this non-uniform charge density. And we would like to calculate the potential at this point. Now, how do we do that? We know already how to calculate the potential for point charges. It's just a sum. But we can just divide our system into point-like very small parts. So I just divide my system into very small parts, very small volumes, each having some volume delta V. Different ones are at different positions. And then this is at the point, let's say, R prime. The potential at R prime will be equal to, well, I have some volume at the point R. Its density its charge is given by this. So it is 1 over 4 pi epsilon 0 rho of R d cubed V. Okay, now this is an example of a bad notation. This is the potential, electric potential. This is volume. This is volume. They are the same V. So just to improve the notation a bit, I will use dV, which is the volume, d cubed x, or d cubed R. The volume is just the product of three distances, so that's why we have this d cubed R. Now, just a bit of a notation. This sign, which is not usually an equality sign, by the way, this is usually used to make definitions. Whenever you see such 3 lines, parallel lines, just like an equal sign, this is called the equivalent. This thing is equivalent to this one. It is when you use it when you make definition. So here I'm defining dV, the volume element, to be d cubed R. This is the definition. And here, of course, I have to sum over all these volumes. I had this charge distribution. I divided it into very small parts. And each part has some charge in it. This is the overall factor. I have to divide by the distance. Divide by r minus r prime. And I have to sum over all my point charges. That is each one of these small cubes. I have to sum over all of them. Now, eventually, we will be taking the limit that when the volume element goes to 0, I will have infinitely many terms, each one of which is 0. But that is the definition of an integral. This is d cubed r 1 over 4 pi epsilon 0. No, there's no cube over there. You didn't study volume integrals, right, in calculus? Multidimensional integrals, no. I mean, you don't have to know all the details. The main important thing here is that just know that what we are actually doing. We take all this volume, we are dividing it into very small bits and summing them up. Evaluation of this integral is something else which you will learn eventually. We will not need it. Most of the time, we will just reduce these integrals to one-dimensional integrals before calculating them. You will not need three-dimensional or two-dimensional integrals. Over the volume. First, you have to specify the volume. So just keep in mind that this integral is over the volume. Or in fact, you can say that this integral is over all space. But in most of the space, rho of r will be 0. There's no charge density in most of the space. Of course, this is just part of the answer. Because this tells me what v is as an integral. Now, I have to evaluate this one also. Again, u, the definition was qi vri. This is for point charges. 1 over 2. Well, the charge of each one of these very small volumes is nothing but rho of r times d cubed r. This is my volume element. I'm summing over all r, and this is nothing but my integral. So the final expression is a double volume integral. Again, you don't have to know these double volume integrals. You don't have to know how to calculate them. The only thing that you need to know at this point is what they mean. We are just dividing we have our huge system. We are dividing it into very small parts and summing over each one of those parts. That's the only thing you need to know. This one. Q and V, the potential V or the volume V? Okay. This one. Oh, the shape of the potential. Okay. Yeah, okay. So this is our system. So I have, let's put the y-coordinate axis. I put a negative charge over here, a positive charge over here. So my charge distribution doesn't have any symmetry. Now the potential energy diagram, we plotted this as the potential of my system as a function of the position. Let's say x, no, y. This is my y. So it was like this. This is when x is equal to z is equal to 0. I'm just going along the y-axis. Now, we do have a symmetry, by the way. Okay, here I just mean q is larger than 0. Okay. Z, okay. Now you see, okay, we have, is this what you mean? V is equal to 1 over 4 pi epsilon 0 q over r. So it should be symmetric between positive r and negative r. Is that the question? Now, you see, also in your quiz, a lot of you have written that if you remember the quiz question, we had various charges and we had different surfaces. There were a significant number of you who just said that, okay, the electric field is 1 over 4 pi epsilon 0 q1 plus q2 plus q3 over r squared. Now, this is just not one or two. There were many of you who wrote expressions, either this one or similar ones. The same problem appears over here. Now, whenever you see such a formula, remember its history. I mean, what does it mean? I mean, it's not just some symbols over there. They correspond to some physical property in the real world. Now, when you say V is equal to 1 over 4 pi epsilon 0 q over r, you should, okay, so you are talking about a point in space. There's a charge somewhere, let's say here, and you are talking about the potential at this point. And this r over here has nothing to do with your coordinate axis, at this level at least. This r just represents the distance between these 2 points. Not the distance from the origin, nothing to do with your coordinate axis. You have this charge, and this is the point that you are analyzing. That r is the distance, which is independent of which coordinate axis you choose. Now, similarly, when we write the electric field, 1 over 4 pi epsilon 0 q over r squared in the r hat direction, now there's a reason why we put these vectors. They have directions. They represent direction. The electric field is not this one. You have to put the vectors. Now, second thing, again, this has a story behind it, a physical system, where you have, again, you have this point charge over here, a single one, just one. And you are looking at this point, you are trying to calculate the electric field at that point. This r below just represents the distance between these 2 points. Has nothing to do with your coordinate axis. And this r hat is, again, it is just a vector pointing from your charge to your observation point. It is this vector. Let me put it like this. This vector with unit length. Plus, it has a direction. So the electric field has a direction. So if you have more than one charges, we have seen that we have this superposition principle. Let's say I have one charge here, another charge right here, and I'm looking at the electric field at this point. Both of these will create an electric field. Now this one will create an electric field whose magnitude is 1 over 4 pi epsilon 0 q1 over this distance squared, not r squared, whatever this distance is. You can use other symbols depending on your problem. You will have to use other symbols for this distance to distinguish this distance from this distance. These two distances will be different. So you have this Q1 charge here, and you have to divide this Q1 charge by this distance. And now this is in this direction, the electric field. And then you have this other charge. It will create an electric field at this point, whose magnitude will be 1 over 4 pi epsilon 0, Q over this distance squared. It will be in that direction. So you have a vector pointing in that direction. You have another vector pointing in the other direction, whose magnitudes are different. So you have to add these two vectors vectorially. So you cannot just write this thing. Or here just take this V of R and say that it has to be symmetric around x equal to 0. Because these definitions has nothing to do with your coordinate axis. Okay, I always insist that you should first choose a coordinate axis. But in writing law, the physical laws, we always use a form which is independent of your coordinates. Now, of course, eventually, if you want to, let's say, express these distances in a numerical form, you might have to choose some coordinate axis to determine the direction of the electric field or to determine precisely the position of which point you are studying. But at this level, they're just abstract in the sense that they are independent of your coordinates. These should be valid, whichever coordinate systems you choose. But always remember to interpret these symbols. What do they mean? This is not the distance from the origin. At least in this context, this R is the distance of your observation point. You are observing, making an observation here from your charge. It's not the distance from the origin. So let's go back here. Now, in this form, the potential will be at the point R, will be 1 over 4 pi epsilon 0. Let's say that the position of this one is R1. The position of this one is R2. This is 1 over 4 pi epsilon 0. Q over the distance from R1 minus Q over the distance from R2. This is my electric potential at the point R. I'm looking at an arbitrary point somewhere over here. I have to substitute the distance of this charge from that point when I'm looking at the contribution of this charge, and when I'm calculating the contribution of this minus Q charge to the electric potential at that point, I have to substitute the distance of that charge from that point. Now, if you look at this distribution, it doesn't have any symmetry with respect to the origin. But nevertheless, it is symmetric with respect to this point. So if you just exchange, if you put a mirror over here, let's say, the two charges, the position of the two charges will just change. The only difference is that their sign will also change. The same symmetry reflects in its potential shape. If you put a mirror right in the middle, the shape of the potential just takes a minus sign. It's the same shape upside down if you put a mirror right here. So it's still symmetric. Now, this is my real space where I show the charges. This is my potential versus the x. This point corresponds to this point corresponds to this point. I mean, the origin doesn't have to be at 0. It's just how you show it. It's not the real thing. Other questions? Well, symmetry is a general word meaning that if you are talking about a symmetry, it means there's some operation which doesn't change your system. Mirror symmetry is a special symmetry. You have infinitely many symmetries. Mirror symmetry is just one of them. Now, in this case, for example, the symmetry is not the mirror symmetry. You just put a mirror plus reverse the signs of the charges, under which nothing changes. Questions? If you don't have, I will have questions. Okay. So let's start with this one. Suppose we have some surface S, and we are told that E dot ds is equal to 0 over this surface. And somebody comes to you and claims that this implies that E is equal to 0. This is the claim of somebody. A, true. B, false. True or false? Who thinks it's true? True? Okay, 1 true. 2. 3. Who thinks it's false? 1, 2, 3, 4, 5, 6. Okay, if I don't count as many people as hands, I will just ask you to move around. Okay, so all those people who believes it is true, I want in this region of the classroom. All those who thinks that it is false, I want them to move to this region of the classroom. This is A, group A. That is group B. And I don't want anybody left in the middle. This is the information we have. By the way, your friend claims that if this is true, this is always true. Everywhere, the electric field is 0 on the surface. It's a closed surface. Yes. I don't know. This is the group who thinks it is true. That is the group who thinks it's false. So you have this claim that they take a surface and the integral of the electric field on that surface turns out to be 0. And then the claim is that the electric field on the surface is always 0. I mean, don't stay seated here just because you don't want to move, because I will ask you why it is true, or why do you think it is true. And I will ask you to explain why it is false. You can discuss with your friends. When you are silent, we will start discussing all together. Okay, why true? Any volunteers? Yes. You should try to convince these people if you think that you are right. And they will try to convince you. So you should listen to them. Maybe they are right. So, I mean, but the question is, I'm not saying, is it possible that E is 0? The claim is, if this is satisfied, E dot ds is 0 on this surface, then on the surface, the electric field is always 0. That is the claim. It's not maybe it is 0. So your friend is saying that since E dot ds by Gauss Law should be equal to Q over epsilon 0, this tells me that there is no charge. Since there is no charge, there shouldn't be an electric field. Did I understand it correctly? So that's the claim over there. So any objections to his claim? Closed surface. We are talking about a closed. We are not given any information about the charges or anything else. We don't know whether there is charges inside or whether there are charges outside, whether the charges are uniformly distributed or non-uniformly distributed. The only information we have is that we have this closed surface and E dot ds over this closed surface is 0. That's the only information we have. We might have charges outside. We don't know. So you are saying that E will be 0 if there are no charges anywhere. E is 0 if there are no charges anywhere. And only in that case the claim would be true. Is that what you say? Now then you should move to the other side. Because the claim is that this is, if this is 0, then the electric field on the surface is 0 all the time. So any objections to this last comment? He says that according to the Gauss law, this statement says that there is no charge anywhere. Any objections? No, I mean, I just want objection to his last comment. He said that according to the Gauss law, if this is true, there is no charge anywhere. The total. So your friend is saying that if you remember the quiz, in the quiz this integral was still 0, but since there we had several charges distributed around, the electric field was not 0. So let me first translate it. Now, your friend is saying that, okay, even if we have charges outside this region, since the electric field lines created by those charges, they will enter and also leave, they will not contribute to this E dot ds. So just having E dot ds equal to 0 doesn't mean that we don't have any charges outside. We might have a net charge outside, although E dot ds on the surface is 0. Well, the surface is in fact this vector is perpendicular to the surface. So, okay, stick with the first one. So your friend is also making analogy with your quiz question. He is saying that we have this separation of charges inside this volume, but the total charge is again 0. But since we have this separation of charges inside this volume, like a dipole, for example, it's a typical one example, it will still create a non-zero electric field on the surface. It's just at one point the electric field lines will leave the surface, at some other point the electric field lines will come back into the surface, so that at those 2 points we will have non-zero electric fields. Again, I repeat, this condition can be because the E is 0, because there are no charges, then this will be satisfied. But the claim is, if this is satisfied, then this is always true. And this integral will still be 0, so that's you are in group B over there. You have to go there. Okay, why A? Are you convinced already? Now, by the way, I'm just paraphrasing what they are saying. I'm not saying that it is true. Okay, why A? Okay, your friend is not convinced. You should convince him. There won't be any break if you cannot convince him. Somebody else? Okay, he is not convinced. Why are you not convinced? Why? Why not? Which doesn't convince? You don't believe in Gauss's law? Or anybody else who wants to explain why you think the answer is A? Why you don't believe that the answer is B? Yes. It cannot be zero. I mean, if you want to apply the fact that E dot ds, this should be zero at this point, well, the surface is changing its orientation. I mean, I don't think that would be a good way of trying to convince people. Yes, it's a three-dimensional, such a surface, so you again think it's A? No. So you think it's A? So you are losing people. He thinks it's A now. Okay, he didn't hear. True. It's a? So he's saying that we have E dot ds, which is the product of the magnitude of the electric field times the magnitude of this area element times the cosine theta. ds is not zero. If cosine theta is not zero, then the only option is that E should be zero. So that's his claim. Okay. No, we are talking about a scalar product over here. So his claim is this formula just states that the sum of E dot ds is zero, which doesn't necessarily mean every E dot ds is zero. So some of them can be positive, other ones will be negative. No, hold on. You are not free to define the electric field. Electric field will be determined by your charge distribution, which you have no idea about how your charge is distributed in the system. So you cannot define your electric field, just pick one electric field. You cannot just pick one ds. This is a general statement. For any electric field, provided you have the necessary charge distribution to create the electric field, this integral is 0. Inside the surface, true. This is my idea. This is how I define it. Okay, now I want everybody in this group to pick up somebody from that group. Okay, everybody pick up someone. Everybody. And now you are free to go to your chosen person. Convince them. Go, 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 go. I want everybody. I want to see everybody over there.
Bir ile ilgili bir mesaj atmıştım da sonra D'yi yazmadığımı fark ettim benim vektörde. Sonra çözdüm.